Hello and welcome to this presentation related to friction belt drives. This is part 3 of our lecture series, and in this presentation we're going to consider vee-belt drives. I strongly encourage that you review both parts 1 and 2 of this lecture series, as they contain underpinning knowledge on which we now develop the equations applied to vee-belts. Here's a brief overview of the presentation related to friction belt drives part 3. The presentation commences with a brief analysis of vee-belt drives with centripetal effects considered. Note that the vee-belt analysis essentially modifies the flat belt theory we reviewed in the previous presentations. And then 4 questions are reviewed. Question 1 relates to vee-belts. We're asked to find the maximum power that can be transmitted if the belt drive is running at optimum speed, and also find the pulley diameter. Question 2 actually relates to a flat belt, and we've got to find the maximum power that can be transmitted by this single flat belt and the linear speed of the belt, V. Question 3 is a rope belt. We analyse a rope belt the same as we would a vee-belt, and here again we've got to find the maximum power that can be generated by the rope belt if running at optimum velocity, stating the pulley speed omega. And finally, question 4 considers 5 rope belts, and we've got to find the maximum power for this particular system given the parameters in the question. And the parameters this time will state the actual speed, so this belt is not actually running at the optimum conditions. And here are the approximate start times related to the various sections within this presentation. So the analysis of vee-belt drives commences approximately 3 minutes into the presentation. Question 1 commences 8 minutes in. Question 2 19 minutes. Question 3 25 minutes. And question 4 commences 30 minutes into the presentation. Hopefully this will aid your ease of access through the presentation. For reference, here's an illustration of a vee-belt drive. In actual fact, there are 3 vee-belts shown here. Here is the driving pulley connected to the electric motor, and here's the output pulley connected to our machine tool. As mentioned in the previous presentation, vee-belts run in grooves. You can just about make out the grooves pulley shown here. There are actually 3 grooves shown in this particular pulley because we have 3 belts. Let's consider the analysis of vee-belt drives. So reference to figure 6 shown here on our slide. For a V-groove pulley, the normal reaction, labelled as R on our diagram, between the belt and pulley is given by the equation R is equal to 2 multiplied by N, and this is normal force shown here on either side of the belt, multiplied by the sine of angle beta, and angle beta is the semi-groove angle shown here, and also here in a right angle triangle. So in essence what this formula calculates is the vertical component for a right angle triangle shown here. That's n sine beta from our sine function, basic trig. And of course there are 2 such components, one on the left and one on the right hand side of the belt, hence why we have a factor of 2 in the equation. If we now rearrange the equation for normal force n, in other words divide both sides of the equation by 2 sine beta, we can write the equation as a half multiplied by r divided by sine beta. Remember from our previous lecture related to trig equations, 1 upon sine beta can be written as cosec beta. And notice the angle beta is in degrees here. So from our basic friction model, we can calculate the friction force between the belt and the pulley. So friction force is the coefficient of friction, symbol mu, multiplied by the normal force n. And of course again that's factored by 2 here because we have the 2 components either side of the V-belt. We can write the friction force as mu multiplied by r cosec beta. Note the 2 in the numerator cancels with the 2 in the denominator here. So essentially the only difference between a flat belt drive and a V-belt drive relates to the friction force that's generated. In a flat belt, the friction force is simply mu r, which we reviewed in our previous presentation, part 2. But in a V-belt drive, the friction force is actually mu r multiplied by cosec beta. So the friction force is increased by using the V-belt drive. Analysis of V-belt drives continued. So we can now state that the coefficient of friction is therefore effectively increased from mu to mu cosec beta, shown in figure 7 here. In the flat belt analysis, the friction force was simply mu r, but in the V-belt analysis, the friction force is mu r cosec beta. So effectively, the coefficient of friction has been increased from mu to mu cosec beta. If we now refer to equation 12 from our previous presentation, but I've shown it here for reference, and equation 12 includes centripetal or centrifugal effects, it can now be rewritten cosec beta term to the right hand side as shown. So in equation 12 for flat belt drives, the right hand side of the equation had the exponential function e raised to the power of mu theta, but in equation 18 for V-belt drives, the exponential function on the right hand side is raised to the power of mu theta cosec beta. Analysis of V-belt drives continued. If we ignore the centripetal effects from the equation 18 on the previous slide, then the equation simplifies to that shown in 19 here. And again, substituting the mu cosec beta for mu in equation 14 in our previous presentation for the relationship of power, this time from a V-belt drive. So equation 20 here relates to power generated from a V-belt drive, and the only difference between this equation and the equation for a flat belt drive is the cosec beta in the equation. And again, if we substitute mu cosec beta for mu in equation 17 of our previous presentation, which was for maximum power, then for a V-belt, the only difference in the equation for maximum power is again the cosec beta term here. So equation 21 is the maximum power that can be generated from a V-belt drive. Just note for general reference, V-belt pulley designs can be more costly to manufacture than flat belt drives, so they're only required when considered necessary, as they can add additional complication and cost of manufacture. So now we're at a stage where we have an array of equations we can apply to flat belt drives or V-belt drives. So we're going to now tackle some questions where we can start to apply the equations. Let's consider question 1 from our notes. An electric motor running at 1400 RPM transmits power by 3 V-belts. Each of the V-belts has a cross-sectional area of 320 millimeters squared. We're given the total groove angle for the V-belt, it's 45 degrees. The density of the belt material is 1.6 megagrams per meter cubed, and the maximum allowable stress in the belt is 2 megapascals. The angle of overlap on the motor pulley, the driving pulley, is 145 degrees, and the friction coefficient between the belt and the pulley is 0.2. We're asked to determine the maximum power which can be transmitted and also to calculate the diameter of the motor pulley. The answers are stated in the bracket here. If you think you can attempt this question without further assistance, I'd encourage you to stop the presentation and do so now, but I'll overview the full solution on the following slides. So here's question 1, beginning of the solution. I've simply shown a sketch here of the belt configuration. We have 3 V-belts in this design, and notice the total groove angle was 45 degrees, stated in the question here. So that means the semi-groove angle, we label that as beta, is actually half the 45, so that's 22.5 degrees. the cross-sectional area of one V-belt is stated in the question, 320 millimeters squared. So let's extract the information from the question. So from the question, the belt angular velocity was 1400 RPM. I converted that to omega in terms of radians per second here. That's 146.6 radians per second. We know that there are 3 V-belts used in this system. We know the cross-sectional area of one belt is 320 millimeters squared. I've converted that into meters squared here. That's 320 times 10 to the negative 6 meters squared. If you're unsure of that conversion, I suggest use a unity bracket to help you construct the appropriate conversion. The total groove angle for the V-belt, that would be 2 beta, is 45 degrees. So the semi-groove angle, symbol beta, is 22.5 degrees. The belt mass density rho is 1.6 megagrams per meter cubed. That can be written as 1600 kilograms per meter cubed. To calculate our mass per meter, lowercase m, that's simply the mass density rho multiplied by the cross-sectional area of the belt. So inserting the values, the mass per meter of one belt is 0.512 kilograms per meter. The friction coefficient, symbol mu, is 0.2. The allowable tensile stress in the belt, lowercase sigma here, is limited to 2 megapascals. So that's 2 times 10 to the 6 newtons per meter squared. And the angle of lap stated in the question, theta, is 145 degrees, and that's been converted here into radians, so 2.531 radians. Let's just consider our thought processes here, trying to devise our solution. To help, here's a summary of the formulae relating to various characteristics of belt drives, and in particular V-belt drives. Equations shown here specifically for V-belt drives. So what does the question want us to determine? Well, the maximum power that can be transmitted from the system. Let's consider what information we're given in the question. We're given the semi-groove angle beta, we're given the angle of lap theta, and we're given the friction coefficient mu. We will need to determine the tight side tension of our belt, Tt. We have an equation for the maximum belt tension, Tmax shown here, same as Tt. And we can calculate this maximum tension because we know the allowable stress for the belt and we know the cross-sectional area of a belt. So we'll work out the maximum belt tension, which is Tt in this maximum power equation. Also need to determine the linear belt velocity. The linear belt velocity occurs in this equation here. We know the mass per meter length. We can calculate the Tc, that's the centripetal or centrifugal tension in the belt, because we know for maximum power Tc is equal to Tt, which we will know from above, divided by 3. So essentially we can also put the Tt value in here. That will allow us to work out the Tc value, which we'll put into this equation. And then by rearranging the equation for V, we can substitute V into this equation. And that allows us to work out the maximum power that can be transmitted by one belt, and then we'll simply factor it by 3 for the 3 belts in this particular system. And finally, the question wants us to determine the diameter of the pulley. So we could find the radius here, we could double that to find the diameter. We will know now the linear velocity V, we've calculated that to find the maximum power. We know the angular velocity in radians per second, that was essentially calculated from the information in the question. So that will allow us to find the radius, and then we can find the diameter. So that's my thinking step through the process here. Let's now undertake the calculations. So question 1, solution continued. Step 1 here, we're going to calculate the maximum tension in one belt, that's simple Tt. So Tt is equal to the allowable tension strength, sigma, which was 2 megapascals, multiplied by the cross-sectional area of a belt, which was 320 times 10 to the negative 6 meters squared. So that's 640 newtons, and that's per belt. Step 2, we're going to calculate the linear velocity of the belt, symbol V. And we know at maximum power conditions, the centrifugal tension is equal to the maximum belt tension Tt divided by 3. So from above, that's 640 newtons divided by 3. So the centrifugal tension is 213.3 newtons. We also know that Tc is equal to the mass per unit length multiplied by the belt linear velocity squared. So rearranging for V, in other words dividing both sides by m and then square rooting, V is equal to the square root of Tc divided by m. Inserting the values. Our belt linear velocity is 20.4 meters per second. Question 1, solution continued. Step 3 here, we're going to calculate the maximum power that can be transmitted by one V-belt here, or P. So here's the equation for maximum power from one V-belt. Just extracted it from our formula sheet here. Presented in a slightly different format, that's all. So inserting the values for tight side tension, Tt, friction coefficient, mu, is 0.2, angle of lap, theta, is 2.531 radians. I just noticed that multiplying by cosec beta is the same as dividing by the sine of beta. So I'm dividing by the sine of angle beta, which was 22.5 degrees. Notice how we're mixing radians and degrees in this formula, but I've clearly stated theta is in radians and beta is in degrees with the notation here. We then multiply by the linear velocity v and of course divide by 3 from the equation. So evaluating, I'll let you undertake the arithmetic at your own pace. What you should find is the power transmitted by one belt is 6,385.3 watts. And to calculate the maximum power that's transmitted by all 3 V-belts, I've called that Pmax here. So Pmax is simply 3 multiplied by the power transmitted by one belt. So overall, approximately 19.2 kilowatts of power can be transmitted through these 3 V-belts, given the parameters in the question. And just to complete the question, we're asked to calculate the diameter of the pulley. So initially I'm going to calculate the radius of the pulley from V is equal to omega r. Transpose the equation for the radius r. That's linear velocity V divided by the angular velocity. Inserting the values. The radius is 0.1392 meters. And so to calculate the diameter of the pulley, the diameter is simply twice the radius. So that calculates to be approximately 278 millimeters. Question 2. A pulley is driven by a flat belt, the angle of lap being 120 degrees. The belt is 100 millimeters wide and 6 millimeters thick and has a mass density of 1 ton per meter cubed. If the friction coefficient is 0.3 and the maximum stress in the belt is to be limited to 1.5 newtons per millimeter squared, we're asked to calculate the greatest power the belt can transmit and the corresponding linear belt speed. Answers are shown in the bracket here. Here's our summary of formulae, this time relating to flat belt drives to help us think our way through the problem. So we have to calculate the maximum power that can be transmitted, so that will relate to this equation here with the centrifugal tension included. We need to calculate Tt and Tmax. So we can do that because we have the maximum allowable belt tension and we have the dimensions of the belt, so we can find the area of the belt. So we have Tmax. We also need to calculate Tc in this equation. For maximum power transmission, Tc is Tt divided by 3. Once we've calculated Tc, and we know the mass per unit length, effectively given in the question, we have the density, we have the area, we can find the mass per unit length. We can then find the linear velocity v by rearranging this equation, so we'll have v in our equation. We're given the friction coefficient in the question, and we can determine the angle of lap from the information given in the question. Remember, the angle of lap must be in radians. So that'll be our thought process through the question. So if you think you can attempt this question, I'd encourage you to start the presentation and do so now, but I will outline the full work solution on the following slides. Here's question 2 repeated for convenience. So question 2 solution. My apologies, this is my handwritten solutions. I hope it's clear for you to understand the calculations here. So extracting the information from the question, the friction coefficient mu is 0.3. The mass density rho was 1 ton per meter cubed, so of course in kilograms that's 1,000 kilograms per meter cubed. The angle of lap theta was 120 degrees, so I've converted that here into radians to 4 significant figures. Determine the belt area here, area of the belt. The belt is 100 millimeters width, 0.1 meters here, and 6 millimeters thickness. So that's 0.006 meters. That evaluates to 600 multiplied by 10 to the negative 6. Just notice my shorthand notation there. That's actually 600 times 10 to the negative 6 meters squared. The maximum belt tension, labelled as Tmax or TT, is the maximum allowable tensile stress in the belt, which is 1.5 newtons per millimeter squared. 1.5 here. And I multiply that by 600 millimeters squared, because 600 times 10 to the negative 6 meters squared is the same as 600 millimeters squared. You can use the unity bracket if you require to check that conversion. I could have also converted the maximum stress into meganewtons per meter squared, but I chose to convert the area here into millimeters squared because I knew the conversion, that's all. So that evaluates to a TT value, a maximum tension value of 900 newtons. Question 2, solution continued. Here's my calculation for mass per unit length, lowercase m. That's the density multiplied by the cross-sectional area of the belt. So inserting the values, the mass per unit length is 0.6 kilograms per meter. Next, I've considered for maximum power what the centrifugal tension will be. And we know from our analysis in part 2 of our lecture, in maximum power, the centrifugal tension is 1/3 of the maximum belt tension. So TC is the maximum belt tension divided by 3. So that's 900 divided by 3. So TC is 300 newtons. Question 2, solution continued. Now we know the centrifugal tension TC is also equal to the mass per unit length multiplied by linear velocity squared. So rearranging for the linear velocity v, that's the square root of TC divided by m. Inserting the values. The linear velocity for maximum power conditions is 22.36 meters per second. Now we have all the information we need to calculate the maximum power that can be transmitted by this system. So question 2, solution continued. Here's the calculation for maximum power occurring at the optimum velocity v. So from our formula sheet, Pmax is 2/3 of TT. Calculated TT already, it's 900 newtons. The value of mu was given in the question. It was 0.3. We calculated the value of theta ourselves in radians, it's 2.094 radians. And the optimum linear belt speed v was 22.36 meters per second. So evaluating the maximum possible power that can be transmitted, approximately 6.3 kilowatts. Here's question 3. We're asked to calculate the power transmitted by a rope belt drive between two shafts 4.5 meters apart. The pulleys are 3 meters and 2 meters diameter, and the groove angle in which the rope belt runs is 40 degrees. That's the total angle. If the rope has a mass of 4 kilograms per meter and the maximum tension allowed in the rope belt is 20 kilonewtons, we've got to determine the maximum power which the rope can transmit and the corresponding speed of the smaller pulley. We assume the coefficient of friction is 0.2. Answer shown in the bracket here. Let's undertake our thought process here. This is a summary of formulae, this time relating to V-belt drives. Remember, rope belts are analysed in the same way as V-belts, so the formula for V-belts here are applicable to the rope belts. So we're trying to find this particular question. Well, we need the maximum power, P max here. Given in the question the maximum belt tension, it's 20 kilonewtons. We're given the coefficient of friction, and we're given the groove angle, which is 40 degrees. Don't forget the beta value here is the semi-groove angle. We need to find the velocity V. Velocity V occurs in this equation here. And we are given the mass per unit length in the question. We will need to find TC before we can find V. For maximum power, we know that TC is a third of TT, the maximum belt tension. So our solution process here will be to find TC first of all from the maximum belt tension, then rearrange the equation to find the linear velocity for maximum power, put that into this equation. The only thing we're missing now is the angle theta, so we don't have angle theta. So how are we going to find angle theta? Well, in the question we are given the diameters of the pulleys and the center distance. So we have the diameter of the larger pulley, diameter of the smaller pulley, and we have the center distance. So we'll be able to find the minimum angle of lap which will occur on the smaller pulley. So once we've found theta b, we can then put that into this equation. Now also the question wants us to determine the angular velocity of the smaller pulley. Well, as we know the linear velocity from the previous calculation, and we know the diameter of the smaller pulley, we can find the radius of the smaller pulley. So from this equation, the relationship between linear and angular velocity, we can find the angular velocity of the pulley. So that's our thought process through the problem. Hope that helps you with your analysis. I would now encourage you to stop the presentation and attempt question 3, but I will very briefly overview the full work solution on the following slides. And here is question 3 stated again for your convenience. So here's question 3, beginning of the solution. I'm going to let you review the solution at your own pace, extracted the various pieces of information given in the question. And those are the rope belt in this case. Remember that rope belts are analysed as V-belts. We were given the angle 2 beta, total angle in the question, so we can find the semi-groove angle beta. We were given the maximum tension for the belt was 20 kilonewtons, so our tight side notation TT is 20 kilonewtons, 20,000 newtons. We were given the center distance between the pulleys, and we were given the diameters of the pulleys. Question 3 solution continued. Note that the power will be limited by the smaller pulley angle of lap, so theta b to my notation, theta b. So that evaluates to 2.918 radians. Question 3 solution continued. Maximum power TC is a third of TT, so 20,000 divided by 3 gives me the value of TC. From knowing TC is equal to mv squared, I can rearrange for V, find the maximum linear velocity required. Solution 3 continued. And then using the appropriate equation for maximum power and find the value. So 445.3 kilowatts in this particular case. We're asked to determine the speed of the smaller pulley. So we use the equation V is equal to omega r, a relationship between linear and angular velocity. Because we already know V and we know the diameter of the smaller pulley, we can calculate the radius of the smaller pulley. The diameter is 2 meters, so the radius is 1 meter. So we can then evaluate angular velocity B, omega B in this case, in radians per second. I've just converted that from radians per second into RPM. I'll let you review this solution at your own pace. Question 4. I'm going to let you read the question and review the solution at your own pace. The question actually wants us to calculate the power that can be transmitted under the conditions stated in the question. So if we view our summary of formulae related to vee-belts, it's actually requiring us to use this equation. Again, I will let you think through the solution for yourself. On reviewing this slide, I would encourage you to think about the information given in the question, or information that we need to calculate, and then determine the power. So I'd encourage you to start the presentation and attempt question 4 now, but I will show you the full work solutions purely for your reference on the following slides. Here's question 4 repeated for convenience. So here's question 4, the commencement of the solution. I'm going to let you review this at your own pace. Basically here I'm extracting information from the question, converting units as required. Question 4, solution continued. Calculate the belt linear velocity here for the given condition in the question, and calculate the centrifugal tension Tc here based on the velocity above. Question 4, solution continued. Calculating here the actual effective driving torque, Tt effective, which in our formula is the tight side tension minus the centrifugal tension. That's this part of the formula for power transmission here. So inserting the values, maximum tension 900 newtons, previous slide the Tc calculated. So that evaluates the effective driving tension. So now we have all the information to calculate the maximum power transmitted per belt for the given conditions in the question. So inserting the values for the mu, the theta in radians, and the value of beta. Note that cosec beta is 1 upon sine beta, sine of 25 degrees in this case, and that's multiplied by the linear velocity calculated on the previous slide. So evaluating the maximum power transmitted by one belt for the given conditions is about 12.4 kilowatts. Question 4, solution continued. So the total power transmitted for the given conditions for 5 belts, we simply multiply the power transmitted from one belt by 5. So the maximum power this system can transmit is approximately 62 kilowatts. That's for the 5 rope belts. And here's the bibliography used to help generate this presentation, which I hope has been of interest to you. And as always, thank you for viewing.